Hello everyone, my name is Minma Vethi. I am the research scholar of Department of Physics, Bhattadev University. This work has been done under the supervision of Dr. Upakul Mohanto, Department of Physics, Bhattadev University. The title of my presentation is Contribution of Proton Capture Reaction to the Abundance of Phosphorus and Sulfur in FGK star. Here is the table of contents of the presentation. It includes abstract, introduction, basic physical situation, methodology, calculation and result, discussion, and in the last the references. Abstract. Stars evolved because of changes in their composition over their lifespan. After the Big Bang, hydrogen and some amount of helium was the first abundant elements present in the universe. Stars evolved progressively by burning hydrogen first and then helium and then heavy elements. The principle of astrophysics tells us that the universe has a beginning. Hence, whatever the present abundance we found in the or we observe, that condition is same for the early universe as well as in the stars. For the study of chemical evolution and nucleosynthesis, the study of light element abundance is important. In the context of hydrogen burning events, even elements are well understood along with the chemical evolution model and successfully predicts their abundance trends. However, the odd elements and heavier elements are thought to be produced via other mechanism. Phosphorus has only one stable isotope, 31P, and is reported to be produced mostly in stars through the proton capture on silicon isotopes in hydrostatic carbon and neon burning cell. In this work, phosphorus and sulfur abundances has been observed using PCl cycle with reaction proton capture reaction beta decay, and the cycle is ended by a P alpha reaction, and the temperature range we consider is 0.1 to 0.7 gigakelvin for 22 dwarf and giant star, which has metallicity of range -0.55 to 0.2. Now the basic physical situation. We consider the stars are isolated and equilibrium in abundance is attained for all the stars. Also, we consider the canonical model of the star evaluation is valid. That is, stars are assumed to be spherically symmetric with no magnetic field, no rotation, and no mass loss from the surface of the star. The method of convection is the only mixing mechanism working in the convective area. Consider the evolutionary scenario for the burning mechanism of the star, which is actually the elements is produced in the core of the star and is brought to the surface of the star by the method of convection. Methodology. For the temperature range 0.1 to 0.3 gigakelvin, we see that the 34 chlorine shows a beta decay at this range of temperature, but at the temperature range 0.35 to 0.65 gigakelvin, the 34 chlorine shows a P gamma reaction. That's why we consider two cycles. One is for 0.1 to 0.3 gigakelvin and other is for 0.35 to 0.65 gigakelvin. Both cycles are ended by a P alpha reaction, which is from 35 chlorine to 32 sulfur. The generalized equation that governs the evolution of elements via a proton capture reaction or a beta decay is given by Clayton in 1993, where n is the number density, rho v is the reaction rate constant, and lambda k is the decay constant. In terms of mass fraction, the time evolution of any element present in the cycle is given by the equation 2. The equation 2 can be expressed as function of hydrogen mass fraction, and it is represented in the equation number 3, which is a series of first order simultaneous linear differential equation. This equation is irrespective of time. That means equilibrium in abundance is attained. Abundance by mass fraction can be obtained of any stable element x with respect to Fe using the following expression, where x by Fe is equal to x by h minus Fe. The abundance is calculated using the following equation, where epsilon of the any element X is equal to X by Fe plus Fe by H plus 6.17. From the equation 2, after converting to equation 3, which are basically a 5 simultaneous differential equation, and we solve the differential equation using computer software. The initial condition we considered, the elements of mass fraction of hydrogen is 0.7, helium is 0.2995, and the heavy element is 0.005. So that X hydrogen plus so that elements of hydrogen plus elements of helium plus elements of heavy element is always equal to 1. Here is the abundance plot with respect to temperature at different hydrogen mass fraction. The estimated abundance ratio of 31P and 32S is present in this table. The data of the first 3 and 4 column is taken from the published work which has been studied using spectroscopic analysis, and column 5 and 6 is our calculated value using theoretical analysis. Here is the comparison between calculated value and the observed abundance ratio for 31P and 32S. The first graph is the abundance value of 31P with the error bar plot, where the open circle means our work and the solid circle is the published work from the spectroscopic analysis, which is also same for the sulfur 32. Discussion. This work we studied the distribution and production mechanism of light and heavy elements in metal poor stars. We have taken the PCL cycle to explain the abundance of phosphorus and sulfur which are observed in metal poor FGK star. Here we found a strong correlation between the observed and estimated phosphorus and sulfur abundance. For the phosphorus, the correlation coefficient is above 0.7, and for the sulfur, the correlation coefficient is above 0.8. Here is the references. Thank you.